Hey, what's going on everybody? This video we're going to be talking a little bit about backtracking and how we can create a program to solve a maze. Now, obviously this is a hands-on series and we're using a chalkboard here, but I think that's fine because at the end of this video we're going to get a little bit hands-on just practicing with multi-dimensional arrays because we're going to use those in this little project we're building. And in the upcoming episodes we're going to build this program to solve a maze. So in order to think about this, what you want to do is just draw a maze. All right, so we have this terrible looking maze here. And let's say you're looking for cheese. And I say cheese because some people will use the example of a mouse trying to find some cheese. And it's basically going to try the different possibilities. And if it doesn't work, it's going to say, nope, I'm not going to do that way. So you start here, and let's say the cheese is right here. So that's the cheese, that little triangle. And what this is going to do is we're going to follow this path. We're going to go down. And at this point, we have the option of going forward or left. And it doesn't really matter which one. We're just going to choose one. Let's say they go down and then they go right and they realize, oh, we hit a dead end. Then what we're going to do is we're going to backtrack to wherever the last intersection was. So right here. And instead of going down this time, we're going to go left. And at this point, same exact decision. We could go straight or we can go up. Let's say we go up. Let's say we go straight. So we keep going and we ignore this path for right now, but that is also an intersection. If for some reason all the other paths didn't work, we could go back to that position and try up. That's the whole concept of backtracking. So at each one of these intersections, it's a position where we have to try numerous different ways. Some people will create algorithms to use recursion. And what this is when a method or a function will invoke itself, and at the end it'll keep doing that until it finds the result, and then it will return ultimately back to the start. So it looks something like this. A method call inside of a method call inside of a method call until we get the result, and then it returns up the layers until we get back to the start. We might look into recursion in a couple of videos, but you don't have to use recursion. You can just use loops, which is what we're going to start with, which in my opinion is way easier. I don't know why people default to recursion for stuff, because I don't think most people logically think recursively. So we're starting off in the console. We're not going to have a graphical user interface for a maze and be able to see a mouse go through it, although that'd be cool. Maybe that's something we can do in the future. But for now, we're just going to have some representation of a maze in text, and we're going to be using the console. So how can you represent a maze? One way is with a multi-dimensional array. So it might look something like this, where we create an array and give it a name, and we open that array, and inside of this array we're going to have other arrays. So it's going to look like this. Let's say we have 3 arrays. This is what the structure might look like. And you can use different numbers to represent a path, a wall, or the destination, which would be the cheese or the exit, whatever it might be. So it might look like this. And let's say 0, this is a wall. 1, this is a path. And 2 is the destination. And then you determine somewhere to start. You could do that in a separate variable, or you could use a separate number. However you guys want to do that. I'll just say we're going to store that in a separate variable and say we start right here. So we're already at an option where we have to decide if we want to go right, down, left, or up. So what we do in code is we basically write code for all of these different possibilities and determine if we're going to continue going. So let's say we start going right, and then the whole process repeats because we're in a loop. So now we're here, and we say, do we want to go right? Well, we actually can't because it's a wall. So the next logical thing would try to go down. So we'll go down, then the same exact thing is going to happen here. We're going to go right, and then we're going to try to go right again. Doesn't work, so we'll try down. That works. Then we're going to try right. Doesn't work. We're going to try down. Doesn't work. And then we're ultimately going to try left, and we'll find the destination. So that is how you can logically think about how this application is going to work. If we're in the situation where, let's say we take a path like down and then left, and we can't go anywhere else from there, well, that's going to be marked as an invalid path, and we will backtrack back to this position, and then we can try going right, or we could try going down, and so forth. So kind of think of it like each time we make a step, we add that to a collection, which is why we've been studying collections. Yeah. And this type of collection is going to be a stack. So let's say we make this final step to right here, and we realize it's not okay. It's not going to get us to the result. So what we do is we say, oh, we don't want to be there anymore. We backtrack by popping that off the stack, which translates to moving back a space in the maze. And then we could go right by adding a position, or if we came from up, we could pop off again to go up. It depends on where you came from and where you want to go, how this is going to work. But we're going to use a stack to basically represent our path. So we might use a linked list or whatever collection, it doesn't really matter, but you could call it path. So then you could access each individual step in this path, and you could output it to the console to see the steps we've taken to get to our destination. So I just cleaned this off just a little bit, but I did mention that when you go to a specific spot and you realize, oh, this isn't going to get us to the result, how exactly do we mark it as an invalid path? Well, what we can do is we can just mark every single place we visited with a particular number, because if we don't want to go down that path again, all we would have to do is label something as a 0. Because if you remember, a 0 is a wall. So you can basically say, we don't want to go down that path, so think of it as a wall. So if this doesn't work, we could label it as a 0 by updating the array. So the array we're working with, we can hard code it in our code like we're doing now, or we could read it from a file. That would be pretty cool, because then you could have a file of numerous mazes and basically say if each one could work, and people could submit these really large mazes, and we could solve them really easily with our maze solving program, say if there's a possibility or not. Very high level, it might look like this. We'll just call a method check maze, and if it's true, if it works, then yes, there is a path. If it's false, then no, there is no path. That's how you can think about our code from 1,000 feet, what it's going to do. And then for the actual maze, you can pass that in from a file, and the program will just tell you if there's a solution or not. And maybe it'll even tell you the path. So this is what our goal is. In order to do this, what we need to do is we need to have a pretty good understanding of multidimensional arrays, and that's what we're going to get a little bit hands-on with now. So get ready, let's start typing stuff out. So I just wanted to talk about some of the key things you might want to know when working with multidimensional arrays, because I don't want this to become a hindrance when we start working with the maze. I already want you guys to have a pretty good understanding of how arrays work, as well as two-dimensional arrays. So this is code from previously. I'm just going to obliterate that, and what we're going to do is we're just going to create an integer array like so, and I'll zoom in since here. Do we really need all these now? I'm going to get rid of them. Give it a name, so we'll just call it M. Why is naming stuff so hard? We'll just go with data, and all we have to do is do this. Oops. We open one large array with these curly braces here, close them here, end it with a semicolon, and then inside of that array we put other arrays. So we can put some data in here just to get some practice. All right, great. Now, if you want to access a particular element, such as this 40, I'll show you guys how to do that. We can output the value and we just say data, and then we use 2 squares. The first square is going to be the row, and then the second square is going to be the column. So we want this one here. So not this one, but this one. And it's 0 based. So the first row is index 0, the second row is index 1. So we want a 1. First column is 0, 1, and then 2. So we want a 2. Whoops, no. 2, not a 3. All right, so put a 2, run this, and see that we get the value 40. So that is how we access particular elements, and you can also change elements this way as well. So if you say data 1, data 2, and we assign it the value 39 or 49, that's fine. Apparently I can't type numbers today. Run that and you can see that new value is 49, so that changed the array. Now you're often going to want to iterate through this collection, this 2D array, and I'll show you guys how to do that using for loops. Here's what it's going to look like. You're going to say int I is equal to 0, I is less than data dot, I can never remember, dot length I++. And then in here, this is going to, for each iteration of this loop, it's going to be a new row. So the first row, and then the second row, and then that third row. So just to see this, we could say sys out, and we could say row index plus I. Run this, you get row index 0, row index 1, and row index 2. I mean, it's really just a variable with a value, but we can use that to reference a particular row. So it's very common to once we go with this outer for loop through each of the rows, doing it again for each of the values of that row, or the columns you can think of it as. So to do that, we're going to use another for loop. All right, and in here we're going to say int j is equal to 0, j is less than data dot length, and this is not quite right. Just to warn you guys, I'm going to come back and look at this length here in a second. J++. So make sure you're using J for all of these. Now let's talk about this length here. So data.length is going to give us the number of rows, but it doesn't necessarily have to be square. You can see there are only 3 rows, but there are 4 columns. So this is not going to give us the correct value. So what you might do is you might grab the first row and see how long it is. So you could say data index 0 dot length. And if you just want to see what both of those are real quick, we can do a sys out and say data dot length and data index 0 dot length. Run this and we get 3 and 4. So we have 3 rows and 4 columns. Now we can actually improve this one step further because each one of these rows does not have to be the same length. So I could go in here and add a couple elements for one of these and that's totally fine. This is interesting because all 2D arrays in Java are what are known as jagged arrays, meaning you can create any size. So we have to account for that. And in order to do that, we don't always want to reference the first array here's length because we're going to get 4. But this one has much more. So we need to figure out how can we grab each row's length for each iteration. And to do that, instead of using 0 here, all you have to do is use I. If you use I, the first iteration, it's going to be 4, the next iteration it's going to be 8, and then the next iteration it's going to be 4. So what we can do now is we can say sys out, and we're going to grab data index I for the row, and then J for the column. So this first outer loop is going to grab the row, then the inner loop is going to grab the column. So let's run this. And it's going to look a little funny. Let's not do a print line, let's just do a print. And then after each one we could do just an empty line. So just like that. Run this. The first 2 outputs, let's get rid of those. That's confusing. I was like, what is going on? Run this. Now we get 4, 6, 3, 10. There's no spaces here, so it looks a little funny. If you want, you can add a space. Run this, we get 4, 6, 3, 10, and so forth. It looks like it matches the array exactly. So this is the technique to iterate through a 2D array. And if this is new to you, it's okay if this is like super confusing. The first time I was trying to iterate through a 2D array, I had absolutely no idea what was going on, and it took me a long time to understand. So be patient with yourself, and just remember to try to have fun. We're gonna go over this again when we go through our maze program, so don't be too concerned about it. And if you can't get your code to compile, here's what I'm gonna do. I'm going to commit this to a repository. So I will say git add, and we'll go my sweet program, source, mysweetprogram.java, and then you can see we'll just commit this, working with 2D arrays. And I'll push this to my GitHub, and you should be able to access this online. So it looks like it worked. So if you go to github.com/Caleb Curry, and then repositories, you should be able to find 30 days of Java. And then you can go to the commits and find working with 2D arrays, and that'll show all of the code for this example. So here's what we added, and here's how we iterate through that. So cool, thank you guys. Hopefully that was helpful, and hopefully you're ready to start creating this maze solver. If you want, you can jump into that right away, or go and review some 2D array stuff as well as backtracking. And maybe look into a little bit on recursion, because we might get into that as well. And that is quite challenging. So I'll see you guys in the upcoming videos. Peace out.